Hello everyone, my name is Harsha Kokel. I'm a PhD student at the University of Texas at Dallas. First of all, I would like to apologize for the inconvenience that we have caused. Due to an emergency, we were not able to travel to Sweden and attend the conference in person. We would like to express our gratitude to the conference chairs for allowing us to present our work online and to the session chairs for accommodating us. So let me get started. Today, I'm presenting our paper, Hybrid Deep RePReL, which is integrating relational planning and reinforcement learning for information fusion. This is joint work with Nikhilesh Prabhakar and Dr. Sriraam Natarajan from UT Dallas, Dr. Balaraman Ravindran from IIT Madras, Dr. Eric Blasch from Air Force Research Lab, and Dr. Prasad Tadepalli from Oregon State. When sequential decision-making problems are formulated as MDPs in reinforcement learning, it is usually assumed that the observation is homogeneous and obtained from a single source. Consider a simple taxi domain here in a simple grid world. We have two passengers, one at red location and one at yellow location. And we have this agent, which is a taxi. And the task is for the taxi to navigate in this grid and transport passengers, say P1 and P2, to their destination location. In a reinforcement learning, in a standard reinforcement learning, it is assumed that all the information about the passengers pickup location, passengers drop location, taxis location, the grid, everything is coming from a single source. But in real life, we see that the bits and the pieces of the information are coming from different sources. So passengers pickup and drop location might come from passengers phone. Driver's current location might come from, say, driver's phone or car, and the grid or the map of the region is actually coming from some third-party API. So the data is coming from different source of information, different sources, and not only that, it might have different modality as well. So we are motivated by the scenario of the real world, and we address the following problem. Given a sequential decision-making problem with a combination of structured and unstructured data, how do we develop a hybrid architecture that learns to act in such domain? In context of this work, we use the term structured data to denote the type of data that can be represented in a symbolic form, that is a tabular data or predicate logic data or knowledge graph, where it is easy to associate some semantics with the data. And we refer raw free-form data like text, image, or audio as unstructured data because it is difficult to adhere to a structure in such domains. So going back to the previous taxi example, we see that the passenger detail might come as structured data from passengers' phones, but the taxi location or the or geography might come as an unstructured data, some image or some heat map, etc., or things like that. In our experiments, we use predicate logic representation for the structured data and image representation for unstructured data. Uh, Predicate logic representation is shown to be equivalent to a relational database and graph database. So any data that is represented in a graph or relational DB can be equivalently represented as predicate logic. So we think this is a good representation to start with. Our current work is heavily influenced by our previous work called RePReL at ICAPS 2021. So let me spend some time describing our framework. RePReL is a hierarchical framework with three major components: a symbolic planner, a abstraction reasoner, and a reinforcement learner. So symbolic planner at the top provides a sequence of high-level subgoals for a given task. So in our taxi domain, the task of transporting P1 and P2 is decomposed into a fourth subtask by the symbolic planner. So here in this case, it is pick up P1, drop P1, pick up P2, drop P2. Symbolic planner decomposes the task into these subtasks or sub goals, but it does not know how to achieve those goals. So we learn RL policies that can explore the environment and learn how to achieve these sub goals. Here we have two different RL agents, one for pickup and one for drop. So essentially, instead of learning a single RL agent that transports both the passengers, we are learning two RL agents, one which is learning how to pick up and another which is learning how to drop. So the symbolic planner provides us the compositionality in the domain, and learning different RL agents for each subtask allows us to use task-specific state representations. What I mean by that is, for example, in this domain, if the RL agent is performing pickup task, it does not need to know where the drop location of the passenger is. It only needs the information about the passenger's pickup location. Similarly, a drop agent does not care about the pickup location of the agent. It should only care if the passenger is in the taxi or not. So we introduce abstraction reasoner here, which uses dynamic first order conditional influence statements. These are influence statements between different state variables that allows the reasoner to reason about what state variables are influencing the reward function or the transition dynamics, so that only those variables are used in decision making. We extend the RePReL structure to something called a hybrid deep RePReL. And in this extension, we majorly change four things. First is we add an input preprocessor that allows us to process the unstructured data. In our experiments, we use CNN network for processing images, but we can use LSTM or transformer for text data and so on. Second is we extend the defussize statements, the dynamic first order conventional influence statements, to allow latent predicate. What this does is it allows abstraction reasoner to work as it is. So the latent predicates represent the unstructured data, and the abstraction reasoner can work as it was working before and reason about what state variables or the state, what predicates are relevant for the current task. Once the abstraction reasoner provides the relevant set of predicates, the merge module would replace all the latent predicate with the embeddings from the input preprocessor. So now we have this combined concatenated representation of the structured predicates and concatenated with the embeddings of the unstructured data only if it is relevant. So such representation is then sent to such state representation is then sent to RL agents, which learn how to act in the domain. So this is the high level architecture of hybrid deep RePReL, which we call HD RePReL. And the learning procedure is as follows. So first we initialize buffers for different RL agents, and we get a high level plan for the current state in the environment. Then for each sub goal, note that the symbolic planner would decompose the goal into sub goals, and then for each sub goal, we perform this loop till either the sub goal is achieved or the number of steps exceed a fixed value. So what we do is we get the abstract state and then get the policy of the current sub goal, take a step in the environment using that policy, and then observe the reward. And we add this SARS tuple, state, action, reward, and next state tuple to the respective buffer. After enough After enough such samples are accumulated in the buffer, we update the sub-goal policy or the RL policy using samples from the respective buffer. So we do a end-to-end learning for input processor and the respective RL agent. In our experiments, we evaluate the sample efficiency and generalization across objects. We use two different domains for our evaluation. First is the taxi domain that I described earlier. We see that using our hybrid approach, RL agents require significantly less number of steps in the environment to learn the optimal policy. And we also evaluate our agent for a generalization across objects. That is, first we train the agents to transport one passenger and then test them to transport two passengers and so on. And we see that the hybrid approach that we propose is significantly better at generalization than learning an end-to-end DQN model. Second domain that we use is a craftsworld domain. Here, there are different tasks like making bread, building a house, breaking a rock, and multiple things like that. This is inspired by the Minecraft domain. And we see that even in this domain, we see, for different tasks, hybrid approach works better than learning an end-to-end neural network. So to summarize, we combined the symbolic planner with the deep RL agent for information fusion. We provided a batch learning algorithm for the RePReL framework. We demonstrate sample efficiency, that is significant reduction in the number of steps required by the model. And we also demonstrate efficient generalization over different number of objects. And we provide hybrid approach for structured and unstructured data. Thank you for listening, and I would be happy to answer any questions. You can reach me at harshakokel.com or harsha_kokel Twitter handle, and you can read more about our work at our lab's website, and you can scan this QR code for more information. Thank you.